Hi, I'm Brandon Johnson.
And I'm James Haas, and we are doing our capstone project on the Fukushima Daiichi nuclear accident.
So I'm Brandon Johnson. I'm currently active duty in the Navy in the nuclear power program. I've been in the Navy for the last 23 years. My last sea tour was on board USS Carl Vinson, CVN-70. I was qualified engineering officer watch and propulsion plant watch officer. And I'm currently stationed at Nuclear Regional Maintenance Department in Norfolk, Virginia. I'm the deputy director of the department. And when the Fukushima Daiichi nuclear accident occurred, I was serving on board the USS Carl Vinson, and that was back in March of 2011.
Okay, and I've been in the Navy 10 years. I joined the Navy in 2002. I did my power school and prototype tours in Charleston, South Carolina. From there, I was stationed on board the USS Nimitz in San Diego, California for a little over 4 years. Did 3 deployments. There I was qualified leading engineering laboratory technician. I was a dosimetry supervisor and worked in reactor training for a little while. From there, I transferred to Norfolk, Virginia, also to Nuclear Regional Maintenance Department, where I qualified supervisory radiological controls technician. Just covered complex radiological evolutions. I was deployed to Fukushima on March 17th, 2011.
During this presentation, it's my objective to walk you through the sequence of events that occurred on March 11th, 2011.
And I'm going to talk about the contamination levels seen on Navy personnel that provided support to those in the disaster area and their expected exposure.
And this image that you see was taken prior to March 11, 2011 of the Fukushima Daiichi nuclear power station. You see 6 reactor buildings, reactors 1 through 4 in the south and reactors 5 and 6 in the north. This is an overhead view of reactor buildings 4, 3, 2, and 1 prior to March 11th, 2011. The Tohoku earthquake on March 11th, 2011 caused a massive tsunami which resulted in flooding of the Fukushima Daiichi nuclear power station and led to a loss of all AC power. A typical reactor plant layout. The major components are the reactor pressure vessel, the primary containment vessel consisting of the steel containment vessel, the concrete shell or dry well, and the wet well or torus, and the secondary containment, which is the reactor building. At the time of the Tohoku earthquake, reactors 1 through 3 were at full power, supplying electricity to the distribution grid. Reactors 4 through 6 were in a cold shutdown condition for maintenance. At 14:46 on March 11, 2011, the 9.0 magnitude Tohoku earthquake struck off the east coast of Japan. Ground motion tripped the seismic sensor set points, causing reactors 1 through 3 to scram. External to the site, AC power was lost due to damage to transmission lines. All emergency diesel generators started, came up to speed, and assumed electrical loads, with the exception of 4 Alpha, which was down for maintenance. There are different cooling systems for Unit 1 versus Unit 2 and 3. Initially, all core cooling systems started for the removal of decay heat. For Reactor 1, it was the isolation condenser system. For Units 2 and 3, it was the reactor core isolation cooling systems. In addition, the high-pressure coolant injection systems for Reactor 1 through 3 started to supply additional makeup water to keep the cores covered. The purpose of the isolation condenser system is to remove decay heat when the reactor pressure vessel is isolated from the turbine condenser. Primary steam is bled from the reactor through motor-operated valves to 2 seawater heat exchangers. Electric motor-driven seawater cooling pumps supply the cooling water to condense the steam. The cooler primary water then returns through motor-operated valves to the suction side of the reactor recirculation pump and into the reactor pressure vessel. The purpose of the reactor core isolation cooling system is to remove decay heat and supply makeup water to the reactor pressure vessel when isolated from the turbine condenser. Primary steam is bled off the reactor through motor and hydraulically operated valves to the RCIC turbine. This steam drives the turbine and is exhausted to the suppression chamber within the wet well. The turbine drives the RCIC pump, which takes a suction on either the wet well suppression chamber or a pure water storage tank to pump makeup water through motor-operated valves to the feed water header and back to the reactor pressure vessel to maintain reactor water level. The purpose of the high-pressure coolant injection system is to supply makeup water to the reactor pressure vessel when it is isolated from the turbine condenser to maintain reactor pressure vessel level. It is 7 times the flow rate of the makeup portion of the RCIC system. This system operates similarly to the RCIC system, but has a higher makeup water capacity. At 1537, the first of several tsunami waves struck the power station. This resulted in massive flooding of the site. Due to the inundation water level, the emergency diesel generators, seawater cooling pumps, power and control boards, and electrical distribution systems were severely damaged and/or grounded. This resulted in a complete loss of all AC power to the reactor plant components. At this point, the emergency decay heat removal and makeup water systems previously discussed all shut down, with exception of the reactor core isolation cooling system for Unit 2, which maintained partial DC power. There were no indications of any reactor plant parameters available in the control rooms. The capability to remotely control motor-operated valves in the isolation condenser, reactor core isolation cooling, and high-pressure coolant injection systems was lost. There was no lighting in the control rooms, with the exception of flashlights. For Units 1 through 3, the operators and workers took the same overall actions to combat the loss of all AC power casualties. At this point, the safety relief valves were lifting due to pressure increasing in the reactors due to a lack of decay heat removal. The reliefs exhausted primary coolant, steam, and hydrogen into the primary containment vessel wet well. This was causing primary containment vessel pressure to go up. The limit was around 100 pounds per square inch. The automatic depressurization system, otherwise known as safety relief valves, protected the reactor pressure vessel from overpressure by relieving to the primary containment vessel. The operators knew that they would have to vent the primary containment vessel to prevent damage. This would allow primary steam, coolant, and radioactive isotopes out of the primary containment vessel and into the reactor building. In parallel, the operators were working on plans to inject low-pressure water into the reactor pressure vessel to restore water level. But first, they had to depressurize the reactor pressure vessel to below 100 pounds per square inch so the water could be injected via portable pumps. These plans were complicated by the loss of power. All valves were having to be operated manually or by the use of portable batteries in the case of motor-operated valves and portable air compressors in the case of air-operated valves. The teams of operators sent to operate these systems were met with many challenges, to include multiple aftershocks, flooded spaces, lack of lighting, and high radiation conditions due to reactor pressure vessel water level lowering and active fuel regions slowly becoming uncovered. Core damage began occurring in Unit 1 within 4 hours of the earthquake. Operators were only able to keep high-pressure coolant injection running for a short time with portable batteries. The operators were able to start injecting low-pressure fresh water at about 05:45 on the morning of March 12th, but core damage had already been occurring for over 10 hours. At about 14:30 on March 12th, nearly 24 hours after the earthquake, the primary containment vessel was successfully vented to the reactor building. 1 hour after the venting took place, a massive explosion occurred due to flammable hydrogen concentration. This explosion caused 5 injuries and hampered further efforts to inject pure water and seawater into the reactor pressure vessels.
Evacuation zones were established following the accident. Areas within 20 kilometers were designated as restricted areas and evacuated. Areas outside the restricted zone with elevated radiation levels were also evacuated. You can see here the actual zones that were evacuated. Certain areas within 30 kilometers and less than 20 rem per year were designated as an emergency preparedness area. Personnel were prepared to evacuate if necessary. The image on the left is of the zones when they were established on April 22, 2011. On the right is when they were reevaluated August 8, 2013. Over 146,000 people were evacuated per the government orders. Originally, the evacuation area was 3 kilometers, but later revised to 10 and 20 kilometers within the same day. This affected the general population greatly. Most only packed the bare essentials, thinking they were only going to be gone a short period of time. On March 15, 2011, residents within the 20 to 30 kilometer range were ordered to shelter in place. This was later revised and changed to a voluntary evacuation. It is unknown when many of these personnel will be able to return to their homes, since contamination levels are primarily from cesium-137 with an approximate half-life of 30 years.
Unit 3 was the second reactor to experience core damage at about 44 hours after the earthquake. The operators were able to keep reactor core isolation cooling system in operation for about 21 hours, and then it shut down. After reactor core isolation cooling shut down, high-pressure coolant injection was able to be initiated for about 14 hours. The primary containment vessel was vented at about 0920 on March 13th. Freshwater and seawater injection started that same day. At 11:01 on March 14th, an explosion occurred in reactor building number 3 due to the hydrogen concentration. Core damage began occurring in Unit 2 at about 77 hours after the earthquake. The reactor core isolation cooling stayed in operation for 72 hours due to DC power being partially available. The reactor pressure vessel was vented to the primary containment vessel, wet well, to allow low-pressure water injection of fresh water and seawater. This venting caused damage to the wet well and allowed depressurization of the wet well to the reactor building, which led to a massive discharge of radioactive material. However, no hydrogen explosion occurred in Unit 2's reactor building. Backflow of hydrogen gas from Unit 3 through the standby gas treatment system to Unit 4's reactor building caused it to explode at about 0600 on March 15th.
Exposure data from Japan and Tokyo Electric Power Company is fairly limited. It's estimated that 167 personnel received a dose greater than 10 rem while combating the casualty of Fukushima. No United States Navy personnel were directly sent into the area to combat the casualty. The surrounding area of approximately 1,800 square kilometers is potentially contaminated with a dose of up to 500 millirem. On average, a person in the United States receives about 360 millirem per year from natural sources in natural background radiation. Exposure from low levels such as these allows cells to repair the damage over time. While an acute dose of 10 rem is higher than normal, it is not life-threatening. According to Idaho State University, an acute dose of greater than 100 rem is needed to experience radiation sickness. Symptoms include nausea, vomiting, diarrhea, and general discomfort. While any dose presents a risk, the international consensus is that a lower dose represents a lower risk. The United States Navy created the Operation Tomodachi Registry as a way to track and document the exposure that the 75,000 Department of Defense personnel involved in Operation Tomodachi received. 4 days after the natural disaster occurred, Senator Murray of Washington contacted the Secretary of Defense and expressed concern over the potential health risk to service members operating in the affected area. This led to the creation of the registry. The registry documents the exposure received at 13 shore-based facilities and 25 ships operating in the area. Personnel exposure at these sites varies depending on their proximity to the accident and their level of involvement. Shore-based facilities vary from 3 millirem in Sasebo to 120 millirem in Sendai. Ship exposure varies from 1 millirem on several vessels, up to 31 millirem on the USS George Washington, and 33 millirem on the USS Shiloh. Pilots were given electronic pocket dosimeters to monitor their crew's exposure while flying missions. Personnel and aircraft were surveyed whenever they returned from a mission. The missions they were flying were related to dropping off humanitarian aid for Japanese locals that were sheltered in place. Personnel contamination levels varied depending on where they flew. Sometimes these levels reached as high as 40,000 micromercuries per probe. Decontamination methods for personnel vary between waterless hand cleaner, soap and tepid water, and damp absorbents. The highest levels of contamination were typically seen on gloves, boots, and the knees of flight suits. A decon laundry was established, and clothes were surveyed before and after laundering. Most clothes would decrease the background radiation levels after washing. Eventually, contamination became fixed in some articles of clothing. Oftentimes, boots had to be removed and aggressively decontaminated with a scrub brush and hot water. Not all articles of clothing and equipment were able to be returned. Oftentimes, this equipment had to be bagged as radioactive waste. The previous 3 photos in the upcoming video are courtesy of Bradley Dunphy.
Alright, let's see how good the boots are. You think this thing's gonna dirty our bucket? Nah. Let's probably just give this one back, it's fine.
It's not NFTP or the
Kind of an asshole kicks uranium. I think that's all we're gonna get.
Overhead view of Fukushima Daiichi Nuclear Power Station after the earthquake, tsunami, and the subsequent reactor plant casualties. I'm Brandon Johnson.
And I'm James Haas.
We hope you enjoyed our presentation.
And if you have any questions, please address them in the comment section on the forum. Thank you.